Okay, can everybody hear me?
Yes.
Oh, sounds good.
Even
Is there anything?
even Delmar came. That's nice. Delmar, you already know all this. Thank you.
Yeah. Yep.
I just came to see whether I can learn something about how to teach people
Ah,
about
okay.
Yeah.
concepts.
Absolutely. I've been watching. I was there for the last two of your lectures, and what we're going to be covering here is similar. I have a somewhat different spin I want to put on it because people are already familiar with the stuff that you did, so I want to throw something somewhat new that might help them latch onto something. But yeah, I've loved your talk so far. It's a really good introduction. So, cool. Is there anything to address before I present?
No, it's up to you, Cameron.
Okay.
If tell people who you are, well, if you want.
Sure, yeah. So my name is Cameron Cianci. I graduated last fall from UConn in my undergrad with a degree in both honors physics and computer science. I've done research before in quantum chromodynamics, quantum cryptography, squid microscopy, and a little bit of optical quantum computing as well in an REU. I currently work as a research scientist at Mirion Technologies, making artificial intelligence for nuclear sensors. So we can get in like spectra and all that stuff, and that's not very relevant to this. But yeah, so I'm basically a Python developer in my day job. So yeah, that's the current credentials I have.
Thank you.
Cool. Yeah. Sure. So I'll share my screen and we can get started. Okay. So I don't know if everybody here has Python installed or any editors or in these lectures in this lecture I'm going to be using Visual Studio's code. A lot of people like Jupyter notebooks. I don't personally use Jupyter notebooks that often, but you can follow along with the code that I'm posting here, and we can have enough time for everybody to write it out, or I can throw my code in the chat as well if anybody needs it.
Cameron, what is it that you use, and why do you prefer what you use?
Sorry, what was the question?
What is it that you use when you're
Sure.
developing your codes?
Sure. So I use Visual Studio's code. I don't know if you can see that right now.
Uh-huh.
Cool.
Uh-huh.
Yeah. So I use Visual Studio's code. I just find it's so to use Jupyter Notebook, I usually go through Anaconda, which takes like 10 minutes to boot up, and it gets kind of annoying. So I just use Visual Studio's in code instead, and it has the sort of built-in terminal functions, so it can help you debug your code. Like if you run your code and there's a bug in the middle of it. Oh, sorry.
But I don't think we see it. I think you were
Oh, no?
that no. We were
Okay. Gotcha. I'm just going to share my whole screen then. So can you see it now?
Yeah. Mm-hmm.
Yep, right here. Cool. So yeah, I use Visual Studio's code, which looks like this. I find it really nice because you can have your code up top and you can run it in the bottom. So I forget what directory this is in. I think it's CD. Yeah, it's Qiskit introduction. So this is we'll see this in a second on the slides. But if you have some sort of a bug in your code and you're running it, you can see the code while you're running it. And then it'll tell you, on this line or whatever, something is wrong, and you can go and debug the code while seeing it run right here. And it all runs right at once. And I don't know, I've been using Visual Studio's code for probably like 7 or 8 years, so I'm comfortable with it. For people who are new to stuff, Jupyter notebooks are usually better because you can run code one block at a time, and that helps people debug it and understand what's breaking where. So, yeah. So that's what I use. Feel free to use it as well. We can, yeah. So I'm going to be doing a quick overview. Sorry, a quick overview of Python for anybody who hasn't done it before. I think everybody here has programmed in Python, but just in case people haven't, or if you're new to Python, I can share the slides with you. Python is really good for. It's really commonly used in lots of different data science applications, artificial intelligence, and machine learning. It's sort of top dog there. And it's also used really commonly for quantum computing. It's sort of a leader in those three. And if you're interested or if you're new to Python in general, you can go click on these. I'll share the slides and you can go click on this link. It's like a few-hour introduction to Python that just basically tells you everything you need to know. So yeah. feel free to click on that later. If you'd like to set Python up and follow along, if you don't have it set up already, just go to www.python.org. You'll see this thing here. You can download it, and then just make sure you add it to your path, which means that you can sort of run Python programs more easily because your computer system knows where to look to run the programs properly. And you can just you can start by running programs through the command prompt, which means you just do sort of Windows, and then you type in CMD, and then this command prompt. You can just immediately, if it's added to your path, you can start programming through command prompt right here. So, and then you can see that we can say Python, and then just start doing whatever you want, like print hello or whatever, and that'll immediately start working. So you can run stuff through the command prompt. You can also install other stuff like VS Code, which we just talked about a second ago, and you can use the terminal there to debug your code in using VS Code while running it in the sort of built-in terminal. And this is the download link for VS Code as well. After you install Python, you also have to write the command in the command prompt, pip install Qiskit to install the libraries. So make sure that you do that as well. And then after that, you should be basically set up to start developing in Qiskit. So also feel free to ask questions anytime during the presentation if you have any questions. I'm open to being interrupted anytime. So cool. So going next, I was thinking it would be nice to do a quick introduction to Python, how it works, and then how compilers work in general, just a quick overview of that, and how a computer actually understands the commands you're trying to send, because we can also parallel that with how Qiskit works with modern computers, with modern quantum computers, which we'll see in a minute. So this is just a really simple Python program that we can take a look at a couple of the different elements. First off, here we have this Python program calculates the square root of pi. The first command here we have is import math, which just imports a library called math. So libraries are sort of pre-written little packets of code that are super useful. You can just use the sort of pre-made code that other experts in the field have already done. They've already made all of this stuff. It's usually really efficient, and you can use it to do a bunch of different things. And there's specialized different libraries for different applications. So math helps you with a lot of different mathematical things, like the value of pi or taking square roots. It's a pretty simple library. Qiskit is going to be the library you're using later, which helps with a bunch of different quantum programming. So first off, inside this library math, we have a value that's preset called pi, which holds a bunch of digits of pi. So inside these libraries, they hold different objects and different values that we can call upon after we import the library. So we don't need to write out all the digits of pi ourselves. This object has already been stored by an expert in the code somewhere, and we can just call upon this value to get it. We'll see that that's similar to some of the circuit objects that we're going to see in Qiskit later. And we also have built-in functions. So in this math library, we can call a square root function, and it takes this square root of pi and it outputs that as well. And we don't have to write our own function of how to take a square root and figure out the proper algorithms and all that. And an expert has already done that, and we can just call upon these functions and store all their values and use them for our own uses. And that's one of the big powers of Python, is its high abstraction. So yeah, any questions on this? Pretty simple stuff. Cool. So how does this program actually run? So this program, after you type out all of your Python code, your computer doesn't like instantly know how to run the Python code. It has to run through a couple steps first to run Python code. And we'll see this sort of paralleled in Qiskit. And this might be an interesting new way to take a look at Qiskit, because you have stuff like control signals that have to be sent to your quantum processor, just like how we're going to have signals sent in our normal classical processor to run this. So we're going to show a couple parallels between sort of classical Python programming and the sort of gate circuit model that you have in Qiskit. So how do normal Python programs run? Well, originally you have your source code, which is the code that we just saw. So that has these high-level libraries of math and all these functions built in and all these objects and values that are already pre-programmed. And it's human readable, so you can read through it and you can understand exactly what's going on. So this is also a really simple example of some source code where you define a variable to be the string hello, and then we just want to add a little exclamation point to the end of it. So that's human readable, but the computer can't understand what that means. If you give this to a computer, it'll think it's nonsense. So what it has to do is it has to run through a compiler first, which this compiler is like a translator that makes the computer able to understand the things that we've written. So it's sort of a human to computer translator you can think of, and it takes this human readable code and it turns it into a series of instructions that are run on your processor. We're going to see this is similar to Qiskit in a second, where we're going to have gates that are run on a quantum processor as well. These instructions are usually a bunch of different low-level classical gates like AND or XOR, or higher level gates like an adder gate, which can add two numbers together. So yeah, overall the flow is we write human readable code, it gets compiled into machine code, which is a series of instructions or gates for the processor to run. So what are these instructions by themselves and how do they work? This might be interesting for people who haven't taken any computer science classes before. So there's sort of two layers, I'd call them, of the sort of machine code area. You have our high level language up here, which could be C, Java, or in our case Python. This gets compiled down to assembly, which these are the individual gates. So this is still somewhat human readable, but it's a little bit more vague. Like this is the command load word, and you have to say, I load this word into a specific register on my processor. So you're sort of moving data from this area to this area. That's what this gate says. It shuttles information from one side of the processor to the other. So you're dealing with a lot lower level features here and a lot lower level gates. These commands end up getting translated through an assembler, because this is assembly code. It gets assembled into an actual machine language code. These are ones and zeros, as they're commonly called, but they're also high and low voltage signals that are sent in your processor that are able to sort of activate or deactivate transistors, and that helps in this case, shuttle our information along. So these ones and zeros here tell which transistors to activate. That helps move our data throughout our processor and perform gates on it. So yeah, for example, we could have this line in assembly, which is add register 9 to register 5. This is a sort of low-level assembly gate that we can have, and we would call this an adder gate. And this is something that you won't have to worry about when you're programming, but it's good to know, specifically for what I'm going to show on the next slide, which is that Qiskit is essentially a quantum assembly language. So normally when you're programming in Python, you can use if statements or for loops or all these built-in libraries that do nice stuff like math.square root that we saw earlier. The gates that you program in Qiskit, like CX gates, are going to be a little bit different than these high-level abstract commands that you can give. These low-level commands are the quantum equivalent of assembly language, where you have to actually tell the processor where you want the data to move and how you want to manipulate it. So similar to how we had an add gate classically, where we added the number in a register number 9 to register number 5, and we got that output. We can now have a quantum gate, which is like the control not gate, where we apply this operation, this quantum control not operation, between 2 qubits in our circuit instead. So when you're programming quantum programs, it's going to feel a little different than programming most other things, because it's way lower level than normal Python programs or C programs or Java or anything else that you might be used to. It's a lot lower level, and we have to keep that in mind. And knowing this will probably help us understand how Qiskit is working a little better as well. Any questions so far? Nice. How many people here are familiar with assembly? I'm curious.
But
Cool.
it's very nice, Cameron. I'm enjoying a lot.
Yeah. Familiar, I know what it is, but being familiar with assembler is complex. So it's
Yep, absolutely. Yeah.
so nowadays it's hard to program there, but I know what it is, and it's good to have a refreshing view on this.
Yep, absolutely. Thank you. Yeah, good to hear. Yep. So yeah, we when we're going to end up making our quantum programs, it's not going to include stuff like sort of quantum if statements. We're not at that level of development in quantum computing yet. It'll involve individual quantum gates, which is going to feel a lot different when you're programming it, and it's going to be a lot lower level. So you have to be careful of that. It won't be necessarily as intuitive as normal classical programming is, because there are people working on that in the industry right now. It's just not very far along yet. So yeah, we can start programming our first quantum program. So if anybody wants to take out their notepad or Visual Studio's Code or Jupyter Notebook, we can start writing out our code now. And feel free to follow along or tell me to stop if I'm going too fast. So I'll give everybody a second to open up whatever they need to open up. Cool. Everybody ready? Everybody good? Sounds good. So the first thing that we need to do is, just like in our normal classical program, we need to import the Qiskit library. So previously we imported the math library, which included a bunch of helpful stuff that we had, like pre-programmed value of pi and the function square root. So we didn't have to write that ourselves. The Qiskit library is going to include a lot more important stuff for quantum computing. One of which we're going to see in a second is our quantum circuit object. Just like how we had a pi object, you can think of it as in our math library, you have a quantum circuit object here in Qiskit. And this is going to include, this object includes its own sort of built-in functions. So you can use this quantum circuit. It's going to have, like, you can use QC dot, like it has gates that we're going to see in a second, but it has all these built-in functionalities that the experts in Qiskit have already programmed for us, and we can just sort of use that stuff rather than having to remake it ourselves. So after you import Qiskit, we need to sort of initialize our quantum circuit. That's step one of the overall making a quantum program is initializing your quantum circuit. So to do that, we're just going to use the Qiskit.quantumCircuit object, and then we can specify the number of qubits and the number of classical bits that are going to be in our quantum circuit. And that's what these lines here do. You could just like this commented outline does, you can just put the for those of you who are new to Python, you can just put the numbers directly in the sort of call to the object itself. You don't need to actually use variables or not. The names of the variables don't matter as long as they're the same. Yeah, some people have trouble with that when they're starting out Python. So cool. Anybody need a second to finish writing this down, or we can go to the next? Okay, let's head to the next one then. So step two is, in my opinion, much more important and something that we should focus on more. And it's also going to be specific to whatever you want to do your research on. And this is going to be the sort of making of the quantum program itself. So those previous lines were just setting up our quantum circuit and our quantum computer, you can sort of think it as. And this part is going to be more specific. This is setting up the specific program we want to run. So just like how we showed earlier with assembly, we're going to have to use these lower level gates to specify what our quantum program is. These low level gates can include stuff like this QC.H gate. Remember, QC is our object that we got from Qiskit earlier. So it has all these really nice built-in functions. Just like math.square root was a nice built-in function, we didn't have to program the square root function ourselves. So we can call this sort of built-in function QC.H, and it will automatically just throw a Hadamard gate onto the index 0 qubit on our computer. And we don't really have to worry about how that works behind the scenes too much. We can just write this down and know that a Hadamard gate has now been applied to our 0th qubit. And then we can add another gate if we want to, like CX gate, which is a multi-qubit gate. And if we put these two together, we make a bell pair, which is sort of like the hello world program of quantum computing. This is what everybody does when they start. So yeah, it's an entangled pair. It's not classical, so it's a nice one to test out how your quantum computer is working. When you're developing your projects, most of your time will be spent on this part right here, adding your gates, figuring out how your gates are going to work. And then also a little bit later, it's going to be spent on post-processing the information that you get from running your quantum circuit. But for the sort of quantum programming part of this project, most of your time will be spent trying to figure out what gates you want to run, reading papers on different algorithms and figuring out how to put those different algorithms into code. That'll be where most of your time is spent. So that's the most important part of your quantum program is this part right here. After we're finished sort of setting up all the gates for our code, we can measure it and get an actual output. So a quantum computer, in quantum mechanics, you're not allowed to just look directly at your wave function. Like, that's a big no-no. So what you need to do is you need to measure your wave function in different bases And then you can output those measurements, which are going to be classical. So that's what these two do. This QC.measure function is a built-in function, very nice. Experts already made it, all that rest of the stuff that I've already said. But this, how it works is you put the quantum bit that you want measured, and then the corresponding classical space where it's going to be put in. So this command here will measure qubit 0 in the poly Z basis, and then it will take that result and it'll throw it into classical bit 0. So it takes it and it moves it over to the classical bit. And then we do the same thing for QC.measure 1, 1. You can also throw in a list of the qubits and the classical bits that you want, and we could just do this in one line as well. Or you can also use QC.measure all. That's also pretty common. So any of those ways are ways to measure your circuit. Cool. Everybody good? Any questions? Cool. Okay. So next up, one of the other reasons why I wanted to talk about assembly so much is because it might make this part a little bit easier to understand. So if we remember a couple slides back, we had that diagram. We went source code to an assembly language to actual machine code. Qiskit already is kind of like an assembly language. So we have to somehow do that assembly language to machine code layer. What I mean by that is we just defined a bunch of Hadamard and C0 gates. And now we have to tell our actual quantum computer how to run those. And that's what this section of the code is about. So we already built our quantum program. Now we're trying to compile and run it. So what we can do here is we need to get first off a backend, which is where we're going to be running it. We have to tell our computer where we want to send this code to. So we can either make an object like I have here, a simulator object. This simulator object will simulate a quantum computer by just doing matrix multiplication and then sampling the output. And so we can call this built-in function qis.aer.getBackend and then our simulator. There actually is a couple other types of simulators you can use as well, like the state vector simulator, where you can actually get out the entire wave function of your quantum computer, not through measurement, but just through viewing the exact matrix multiplication. If we simulate the quantum computer exactly, we don't in our classical computer, we don't need to measure it. We can just sort of output the entire vector because it's stored somewhere on our computer. So you can also use that one. But regardless, once we get our backend, we are going to want to run some jobs on our backend. So we want to take this simulator that we just initialized, or we can also initialize a IBM quantum computer, and we want to run our circuit that we pre-programmed on this backend or on the simulator. And what we do there is we hand the backend.run function our quantum circuit. So this tells us the gates that we want to run. This function right here, Qiskit.transpile, is a little bit harder to explain, but what it does is it basically tries to make the code efficient to run on whatever backend you're running on. So this probably won't be too important for it won't be too important for simulator backends, although it might be able to make the gates a little bit more efficient. It'll be a lot more important for actual IBM quantum computers because they have sort of connectivity problems where a qubit over here might have a really hard time talking to a qubit over here. So if I try to perform a C0 gate between those two, it might be a little bit more difficult. So you can do some optimization and maybe move those qubits closer together and just relabel everything. And that's what Qiskit.transpile does. It understands what backend we're using, and it tries to make our quantum circuit that we programmed as efficient as it can be for this specific backend. And then we also tell it the number of times that we want it, because quantum mechanics is statistical, so we need to get a bunch of runs. Cool. So after using our backend and running our program, we get out this variable job, and this job variable contains a bunch of different stuff, including the results of our run. So we can get the results by just saying job.result, and then it grabs the results of the run, and this is all the different measurement results that our circuit has gotten. And then we can say result.getCounts of our quantum circuit to actually get the individual counts or the measurements that were performed in our circuit. This counts variable is a dictionary. So if you're familiar with Python, it's sort of like a funky list, So so it has interesting indexes, and it looks like this down here. So we can see that first off, up here we printed our quantum circuit. You can just print it like this if you want, and we see our circuit which has a Hadamard and then a control NOT gate, and then we perform two measurements. And we can see the output of our circuit now in this counts object is a list where it says the outcome 1, 1 was reached 510 times, and the outcome 0, 0 was reached 514 times. Which it should be about 50-50, which it is to statistics. So yeah, that's the sort of compiling and running step. Any questions on that? No? Okay. Sounds good. So next up, you can also sort of modify this step a little bit to run on an IBM quantum computer. I don't have an IBM account because I don't know, I don't have the funding for it myself. But yeah, so I looked it up, and these are the sorts of commands that you have to run. You have to load your account. You have to get the different providers, and then from these providers, you can use this function qiskit.ibmq.getProvider, and then you say you want an IBM quantum computer to get that provider. And then on this next line, 73 here, as it's labeled, you can do provider.getBackend, and then specify the exact quantum computer that you want to run it on. So the one that I chose was just IBM Q Vigo, which is one of the quantum computers that they built. And then after this, we get our backend object back. So just like we saw on this slide, we have a backend object here. In this case, on this previous slide, it was made from a simulator, and then we ran all of our jobs on it. In this case, we get it from a quantum computer, and then we can run all our jobs on it. So yeah, that's sure. Yeah.
One question, Cameron, just can you go to the previous one? Because there is something when I try to create the backend with this command, I get some error.
Okay.
An error.
Do you want to potentially share your screen? We can see what it is.
Yeah, of course. Yep. Let me share. Can you see it?
Yes.
The first one, I just tried this and it didn't work.
You don't have Qiskit.aer. So you see the line above that, you say from Qiskit import AER.
Yep.
If you uncomment that, it should work. Because you're pulling in. Does it still not work?
No.
Use the AER provider. Oh, interesting. This is new. Yeah, it works. So it works fine on my machine, which means that I'm guessing that it might be.
But wait a second, Kuro, you have Qiskit installed, yeah?
Oh, sorry. What?
Yeah, that was done at the very beginning. So I ran this, and then I think everything was installed, and then this has worked.
You see, below it was. Below it, okay. I was saying somewhere you can install Qiskit. Where is it? Can you go?
Yeah, the install Qiskit is here, the installation, and here is the import.
But later, it was complaining later. Can I see below?
Yeah.
Yeah, in the bottom, it says here that I don't think you have Qiskit. It says it doesn't like AER. So Qiskit has a bunch of sort of, it's split into a bunch of different sub-projects, one of which is AER, then there's Aqua, and then there's Metal. And they all have different purposes. Like Metal is for making actual superconducting quantum circuits. AER is for sort of this quantum simulation stuff we're seeing here. So it might have pulled in some of the libraries, but not others. I'm not exactly sure.
Not others. Okay.
Yeah,
you
maybe
should run that
libraries.
command. It might work.
That's the law.
Okay. Yeah, it was just this. You can continue.
Sure. Yeah. Yep. Mind if I steal the screen back? Cool. Thank you. Sure. Yeah. Let us know if you get that fixed up, or if you don't. Delmar also put something in the chat where he said that we can use basic AER instead of AER. So maybe try switching that command out.
Okay.
Sure.
I'll try first the install and then the other.
Sounds great. Yeah. Cool. Okay. So sounds good. So let us know if you get that working, or if you have any more.
Yeah,
problems.
you continue.
Okay.
Don't worry.
Yeah. Sounds good. Okay, so my next point is going to be, I split this up into 3 different steps. Step 1 was a setup. Step 2 was the actual quantum gates, and step 3 is compiling and running. My advice is to not memorize steps 1 and 3. because steps 1 and 3 are something that you run or write, or it's something that you have to look up, like when you start a new project, like once a project or maybe twice a project, or whenever you want to switch to a different Qiskit, like if you want to change from a simulator backend to the IBM quantum backend, like the actual quantum computers, you'll have to change that. But for the most part, almost all of your time will probably be spent with the actual quantum gates itself and trying to tune the gates or figure out how to put the algorithm that you're interested in into these gates and seeing what the outputs are. So my advice is to not worry too much about steps 1 and 3. Just write them down once, make sure they run on your system, and then I usually just copy and paste it from one project to another. Like, don't memorize any of these commands necessarily. Definitely understand what the general idea is, but you don't need to memorize this. And the things that most of your attention should be put to is to the actual quantum program itself, which is in 2. Step 3 is just compiling and running it, and step 1 is just setting it up. So the important and interesting and the meaty part of it is all in step 2. So yeah, just copy and paste. That's my opinion. So yeah, you won't have to touch it too much. So the next potential part that we could also talk about is post-processing. So now that we have all of our quantum circuit set up, we defined our quantum program, and then we compiled and actually ran it on either a simulator or a backend. We can take all that data and we can do post-processing. So Python is really good for data analysis. That's one of its big strengths, which is really nice that Qiskit is a Python library. So you can automatically take the stuff that you've written in the first part of your program using Qiskit, and you can get that dictionary counts. And then you can use that counts variable, that's a dictionary, to do a bunch of data processing on it to see what all your results are. So you don't have to write this part down. This is just an example of some post-processing you could do. In this case, I was just showing that since we made a bunch of bell pairs, there should never be the state 0, 1 or 1, 0 because they're entangled, so they should be exactly the same. So I check if there's any counts, if there's any counts that have 0, 1 or 1, 0. And if there is, I say there's a little noise in the circuit. And if there's a lot of them, then I say there's a lot of noise in the circuit. So that's just an example. You can do tons of different stuff with post-processing. These are some of the ways that you can access the actual number of counts in each one, and how you can deal with dictionaries. You can also visualize it using a bunch of different stuff like pandas or matplotlib. This is an example of visualizing it with matplotlib, where we just make a bar chart of the different states and how many counts we have in that state, in each state. So yeah, this is a little example here. This is how you make charts in matplotlib. So yeah, cool. So yeah, the post-processing is sort of the last step that I'd say in this process, and it's classical computing, so it's not the quantum part. You just have a normal programmer. So yeah, that's the entire talk so far. We can go in and check all the code right now and see if we can get it working on people's machines if they have any bugs. And I can also throw my full code in the chat if you'd like to run the code that's working on my machine. I've been programming in Qiskit for probably 4 or 5 years. So my libraries sometimes have troubles that other people's don't, because some of the dependencies and stuff are a little funky. So like, for example, I forget what it was, but there was one command that I was trying to run earlier that wasn't running for me properly because my Qiskit version, even though I updated it, other libraries it was dependent on were out of date. So but we can take a look at each person's individual programs, see if you can run it, and then you can use this as sort of a template code and just change step 2 whenever you want to run a new simulation of some program after you read a new paper or something. So does that make sense to everybody? Yeah.
Yes, this is go on.
Yeah. Just one question. Can you install Qiskit as a part of Anaconda? Is it included in Anaconda? Yes. Okay.
Yep, absolutely. And Anaconda is a really good tool. If people here don't know about Anaconda, it has a ton of different stuff. It's also a giant program, but it has a ton of different stuff. What you'd be using it for in this case is it's sort of virtual environments, which means that you can make a new version of Python for a specific use case. So I might have one version of Python that I want to use for artificial intelligence, and that has libraries like PyTorch and TensorFlow installed. And then you can have another library that has quantum stuff like Qiskit installed on it. Another virtual environment. And then we can separate these two. So there isn't any interaction between them. because sometimes you fight with your quantum version, your Python versions and all your libraries, and let's say, for example, the NumPy library that TensorFlow needs might be different than the NumPy library that Qiskit needs, and that'll cause some problems. So separating out all your stuff into different use cases, where, like, let's say for my example, I do artificial intelligence and I do quantum computing, having 2 different installations of Python for that is really useful. So.
Okay, Cameron, so you can share with us this
Yep.
the presentation.
The presentation, yep.
Yep, absolutely.
You
So
can put it in the Dropbox, or up to you, or you put in the
sure.
chat. And then...
Yeah, I can send it to both. So I can probably send it in the chat.
And if you want to share your code, that's also nice.
Yep, absolutely. Let's see.
I think I'll stop recording, yeah?
Sure, yeah.